this is gonna be an extreme fun to have 8 proofs of this limit. Limit x goes to 0, sin x by x is equals to 1. This is what many of us might know from our high school. And we basically were received a geometric proof on this based on the circle. And the things that x is less than tan x but greater than sin x on 0 to pi by 2, and we used skews theorem. Yeah. So that was how we did in high school. But in this video, we are going to have 8 different proofs of this identity. Limit x tends to 0, sin x by x is equals to 1. So the first one with the gamma function. Yeah, let's begin. Okay, so some of you might not know about gamma function, digamma function. For them, we do have other proofs too. I do enjoy. Just try to understand if you haven't. Okay, so we have limit. Basically, first we want to let here x as n pi, and there are some reasons for it. For doing so, let x as n pi, so that n equals to x by pi, and as x goes to 0, n goes to 0. So we have limit n goes to 0, sine of n pi by n pi. Now we can do something like this. We can take n out, and then we can have 1 by pi by sine n pi. Now I think you know something about this formula, pi by sine n pi. Yeah, this is the reflection formula of gamma function. Limit n goes to 0, 1 by n, and then 1 by gamma n, gamma 1 minus n. Now you might notice that we have n times gamma n over here, so that's gamma n plus 1. Limit n goes to 0, 1 by gamma n plus 1, gamma 1 minus n. Now try to put the limit n at 0, and you get 1 by gamma 1, gamma 1. So gamma 1 is just 1. We have 1 by 1 into 1, so that's 1. And we have proved that this limit in fact equals to 1. So this is our first way. Second way is through power series. So we need to know the power series for sin x. And we have limit x tends to 0. The power series is x minus x cubed by 3 plus x to the power 5 by 5 minus x to the power 7 by 7, and so on, divided by x. So you can basically see where we are going right now. It's just clear. 1 minus x squared by 3 plus x to the power 4 by 5, this is 3, minus x to the power 6 by 7, and so on. So if you substitute x at 0, all of them will go to 0, and only the first term will remain. So that's 1. So we already have 2 different proofs for this one, and now let us just delete them for the sake of space. Yeah, now let's move on to another one. So L'Hopital's rule. It's really easy through L'Hopital's rule. So we have limit x tends to 0, sin x by x equals to 1. So this is in the form of 0 by 0 initially, so you can use L'Hopital's rule. If you use L'Hopital's rule, we will have derivative of sin x as cos x, derivative of x as 1, so that is cos of 0, so that's 1. Yeah, we are done. So third one, now fourth one. So fourth one is based on double limit. So basically we introduce another limit too. Let's introduce limit u tends to 0 and put something like this. So you will know the reason for this. Sine of x plus u minus sine of u by x. Yeah. Now if we interchange these limits, something interesting happens. We have sine of u plus x minus sine of u by x. basically you can compare this with the definition of derivative. So if you have limit delta x tends to 0, f of x plus delta x minus f of x by delta x. So here our x is acting as a delta u, yeah. So x is acting as delta u, and so this is just the derivative of the function. So this should be cos of u. So limit u tends to 0. This is just cos of u, and so substitute 0. We have cos of 0 equals to 1. So we have solved it this way as well. Now let us erase them. So we already have 4 different solutions for this limit. Now we are heading towards other 4. Squeeze theorem. For squeeze theorem, we need to know that in the interval of 0 to pi by 2, our x is less than tan x, is less than sin x. So if you want a logical reasoning of why this should hold true, so let me see. Okay, so when our values of x are going from 0 to 1, let's say we have pi by 2 is 1.57, so pi by 2 over here, and pi by 4 is around 0.7. Okay, so we have pi by 4 over here, let's say. So the x the for x to take value of 1. So when the graph of x like reaches up to 1, and then only its value will be 1. But for tan will already reach value of 1 here, and sine will reach value of 1 only here, sine, and this is just x. Okay, so tan of x increases really fast, so that at pi by 4 it already reaches the value of 1, and x reaches the value of 1 just at 1, and sin x reaches the value of 1 at pi by 2. So we see that sin x is growing really slow in compared to x and tan x, and x is also slow in relation with tan x. So you can see why this works. Now if we have this, we can just invert them first. So we'll have 1 by sin x, and if we invert them, the signs are also going to change. Is greater than 1 by x is less than cos x by sin x. Yeah, now if we can multiply by sin x, so we get 1 is greater than sin x by x is greater than cos x. Now we can take limit x tends to 0 everywhere. X tends to 0, 1 is greater than limit x tends to 0 sin x by x is greater than limit x tends to 0 cos x. Now this is 1, this is limit x tends to 0 sin x by x, and then this is also cos 0, 1. So by squeeze theorem, this should also be 1. Limit x tends to 0 sin x by x equals 1. But through this, we only prove it for this interval, but it holds true for all values too. Okay, that's right. But we only need this interval because our x is going towards 0 and x going towards 0 is definitely contained in this interval, so that works. Now let's go to the next proof. The next proof is about digamma function. So let's go over digamma functions. For digamma function too, we first of all establish the same relation. Okay, so we first of all let x equals to n pi, and then n equals to x by pi. So as x goes to 0, n goes to 0. So we have limit n goes to 0, sine of n pi by n pi. Now for this time we have 1 by n equals to digamma of n plus 1 minus digamma of n. Yeah, so we'll use that thing over here. So we will have limit n goes to 0, digamma of n plus 1 minus digamma of n by times sine n pi by pi. Yeah, I guess that's fine. Now after this, uh, we cannot really substitute 0 over here since we don't know the value. So we can try to make this as some other where 1 is content. I mean, we have a relation that digamma of 1 minus n minus digamma of n equals to pi times cot n pi. Yeah. So you can generally basically use this to introduce this thing. So we have limit n tends to 0 or digamma of 1 plus n, and then we will have minus digamma of 1 minus n, yeah, and then minus pi cot n pi, minus pi cot n pi times sine n pi by pi. Okay, so then we have limit n tends to 0 digamma of 1 plus n minus digamma of 1 minus n, yeah, by times sine n pi by pi. Is that it? Sine n pi by pi. My minus digamma of n is, oh, this is actually plus. So minus digamma n is, if you take this other side, this will be minus, but this will be plus. And after this, we will have, so I multiply this with this thing now, pi cot n pi, and then times sine n pi by pi. Now if we substitute n is 0, we have digamma of 1 minus digamma of 1, yeah, times this is blah 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 plus this is cos of 0, yeah, we have cos of n pi, since this pi cancel out, and cos of n pi, so we have cos of 0 times pi cos of 0. This of course goes to 0, plus this is 1, the limit is 1. So hope you understood the solution. This was a really tricky one, I should say, to get to diagram function and then prove it. So now we have some more proofs which are to be done. Yeah, and I hope you are really enjoying these proofs. Yeah. Okay. Yeah, let's move on. Now next proof is through Euler's formula. Through Euler's formula, it's really nice one. That okay. First of all, we need to know the expression of sin x in terms of e. Yeah. So we can express sin x in terms of e by the following formula: e to the power ix minus e to the power minus ix by 2i, and we have x over here. Now we can just take the LCM to make it e to the power 2ix minus 1 by 2ix, and then 1 by e to the power ix. Now you might notice something. This is a standard formula because these two are same, and 2x is also going to 0. So this is 1. This is a known limit. Limit theta tends to 0, e to the power theta minus 1 by theta. This is actually equals to 1. Yeah. So use this. This is 1, and 1 by e to the power 0, which is also 1. So this is 1. So now we have proved this using Euler formula, and last one is epsilon delta definition. So yeah, but that using epsilon delta definition, it's really easy. So I'm leaving it for my viewers to try the proof of this by epsilon delta. It's really easy, and if you want to solve, do comment down about how you do that. So this was it. We did eight proofs for this limit, and I hope you enjoyed them all. Thanks for watching. Look forward to seeing you in the next video.